Let me share. Okay, so we find 1,3 sigma tropic hydrogen shift. That was what that was. Stop sharing. No. Okay, let me go to this. Okay, this is some problem is there. Let me. Okay, stop share. Then again, I come and share it. Okay, so this is we had done earlier 1,3 sigma tropic shift, right? So this is what happens. 1,3 sigma tropic shift is thermally not allowed, photochemically it is allowed, and thermally it is interfacial. So we find this, so many examples here. Now let us come and discuss this 1,5 sigma tropic shift. If it is 1,5 sigma tropic shift, so this is going to be, this is 1, 1, 1 here, 1, 1. Let me start with this pen and board. Are you getting my voice? Hello?
Yes, sir.
Okay. So 1,5 sigma tropic shift will be this and this an aligning system. This is going to be grounded 1, 1, then 2, 3, 4, 5. So this hydrogen bond will drag and go to 5. So we are getting this product. Now from here, this is an overlap between, if we just go to the theory, this is the free radical that is going to have 5 free radicals. So there will be 5 psi 1, psi 2, psi 3, psi 4, psi 5. And there, first one, the lowest energy will not have any node. Second one will have one node, so that falls in that orbital only. That p orbital only in the middle. Third one will have 2 nodes, so it will be distributed here. Fourth one will have a node here, and fifth one will have a node here, 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 here. So psi 4 will have 3 nodes, 1, 2, 3. So this node falls on the orbital itself. So here the orbital becomes perpendicular to this. So there is no overlapping here. So we find here psi 2 is going to be this. Sorry, sorry, this is going to be opposite. This is going to be opposite. Sorry, opposite of this. So we have here, this is psi 3. There are 5 electrons, so 2, 4, and 5. So the HOMO becomes this. HOMO is this. And this overlap is going to be with hydrogen. So hydrogen atom with its HOMO of hydrogen, that is going to be in this phase, and the terminal phase of this one is having the same. So that is going to be an overlap which is possible. So the bonding is possible. So here, this therefore the thermal 1,5 superficial sigma tropic shift is allowed. So that is what we get from here. Now. So what we find, 1,3 is not allowed thermally, 1,5 is allowed. So what is going to, so if I have one example here, this is going to be 1,5. We can very easily now identify how this 1,5 will be there. Now you can ask one question, why not this hydrogen? Yes, that is also possible. This hydrogen also is going to shift. But we are to have a distinction. We give here deuterium. So the deuterium is shifting to this position. So these positions are identified like this: 1, 1. The bond which breaks, that gets 1, 1. Then 2, 3, 4, 5, and this 1, 5. This is also a 1, 5. And here we have these examples are there with three-membered rings. So three-membered rings are considered to be something equivalent to double bond. Because what is a double bond? Double bond is the pi-electron system where there is a strain from the normal bond is sp3 hybridized, sp3 hybridized, but here it becomes sp2. So there is some strain developed here. So that way, so this molecule is also having a strain. So it can be considered something like a double bond. So if it is this one, then we are having this 1, 5 shift will be there. So 1, 2, so 1, 2, 3, 4, 5, and then this hydrogen is there. So this is the sigma bond that is breaking, and we'll have a new sigma bond here. So it becomes the bonding is between 1 and 5, so it is 1, 5 sigma tropic shift. Now, there is Woodward and Hoffman rule for sigmatropic rearrangement can be summarized like this.
Sir.
Yes.
Sir.
Yes.
Can you explain first one once again?
First one. That
Yes, sir.
This one, right?
Yes, sir. Why
Okay.
1, 5, not 1, 2?
Not 1, 2. All right. So let us see this. Erase this. Okay. Now, what is that system? 1, 2 cannot coma. To me, what is that 1, 2? Why you are telling 1, 2 sigmatropic? Huh? Now,
No, sir.
now
Not
you
1,
see.
2, but 1, 4. Maybe 1, 4, no?
No. You see this. What is the pi electron systems here? We have to go to the conjugated system. This is the conjugation, right? So the whole pi electron systems are involved. Not that it is in the middle. So here it is. So the bond that is going to break is 1, 1. Then 2, 3, 4, 5. So the shift is going to be 1, 5. What is your, just see the theory. Sorry. So what is the system? This is, it is going to be a, what it is going to be? It is going to be a cyclic transition state. The cyclic transition state happens to be here, this H. So what it is, this pi, this is the one that is going to be the system. So this is cyclic. All pericyclic reactions involves a cyclic transition state. The transition state, you have to look for the transition state. I think somebody, all of you, please mute your mic. Once when you are talking with me, then only you put it off on. Some extra sounds are coming. Now, you got my point? Hello?
Yes, sir.
Okay, so this is what. Now here also this is going to be the same way. For only thing difference is that instead of one pi bond, we are having a cyclic ring. So that cyclic ring you should be aware. Now Woodward, we can summarize this rule. Now how this by Woodward and Hoffman. Now here, what we find, if we have a sigmatropic shift of this nature, that is 2 pi bond here, and this sigma bond is going to break, so another 2, so 2 and 2. So what is the system becomes? It becomes an even system. When it is an even system in the allylic system for sigmatropic shift, what we have got, the reaction condition when it is thermal, it is going to be interfacial, and it is going to be forbidden. That means it's not going to take place. Interfacial is possibility is less because of this. That is geometrically forbidden. Means that geometrical transition between 1 and 3 is very, very, because the gap is very small. And photochemically, what we find is going to be superficial, and so it is allowed. So 1, 3, that is why 1, 3 is a system like this, is an even system. When we come to 1, 5, 1, 5 is what? This is 1, 5 system. 1, 2, 3, 4, 5. But how many pi electron systems are, how many electron pair systems are there? 2 is coming from this one, another 2 is coming from here, and another 2 this sigma bond, because always in the sigma tropic shift there will be a sigma bond involved. So these 2 electrons are also. So we are having 3 pi electron system. 1, 2, 3. So 3 pi bond system or 3 electron pair system. So when it is 3, 3 means odd. So when it is odd, the thermally it is going to be allowed and it is superficial, and photochemically it will be forbidden and it is going to be interfacial. All right, got my point? Now, if it is 1, 7, suppose it is 1, 7, 1, 7 system will be something like this. Suppose this is 8, then this is going to be 1, 2, 3. So now tell me if it is one, this is 1, 7, 1, 1, 2, 3, 4. Oh, sorry, what is this? 1, 2, 3, 4, 5. No, sorry. No, sorry, this is not, no. This is not the one. 8. This is, so 1, 1, 2, 3, 4, 5, 6, 7. Now, if it is 1, 7, now you tell me whether it is going to be thermally allowed or thermally forbidden, what it is. Tell me quick. So what you have to look for, whether it is even system or odd system.
Even system.
This is 2, another 2, another 2, another 2. So 1, 2, 3, 4. That means it is going to be even system. And if it is even system, what is thermal? Thermally, it should be interfacial and it will be forbidden. And photochemically, it should be allowed. But 1, 7 is, you see, is a big ring system, right? It's a big one. So here, though it is forbidden, but it takes place because there will be less strain. 1, 3 is 100% forbidden because it is interfacial, but 1, 5, sorry, 1, 7 is though geometrically allowed, but because the what is called the transition state is less strained in interfacial transition, so it is going to be allowed. So this is an example that we'll be finding here. So you get this one. Okay, this is some more examples we have shown. This is going to be a 3-3 sigma tropic shift. This is 3-3 sigma tropic shift we have already taken and will be taking now. This is also going to be a 3-3 sigma tropic shift. There is nothing. Now here, 1-7, we are talking of the 1-7 sigma tropic hydrogen shift is thermally interfacial. So if we compare this one, and transition state is not much strained because of the big size, hence sterically feasible. And this is what we find in the conversion of provitamin D3 to the vitamin D3, which happens in nature. You see here. This is provitamin D3. How do you get provitamin D3? We actually, in our vitamin D is obtained from cholesterol in our system. Cholesterol is converted to, first of all, it is converted to this molecule dehydrocholesterol, from where, this gets converted to this. Again, here, this is also a This is also a pericyclic reaction. Now you see here, these two double bond and this methyl group and hydrogen are in trans position. This is only photochemically it is converted to this. Photochemically it is converted to this. Can you not now how to get this one? This is a because it is pericyclic reaction, electrocyclic reaction. It is going to be a odd system, right? Because the open chain system is going to be odd. So it is 2, 1, 2, 3 double bonds, odd system. So 3. If it is odd, to get trans of this methyl and this hydrogen should come in transposition. If it is if they have to come to transposition, this rotation of this terminal hydrogen, this hydrogen which is there, this hydrogen, and the methyl group, this methyl group which is there, must rotate in con mode, con rotatory mode. Con rotatory mode means this hydrogen, if it moves here, the other one also moves in the same direction. So you just see, or if it rotates in this direction, this also will rotate in this direction. When if you rotate in this direction, what happens to hydrogen? This hydrogen is going down. And methyl group which is there, because it is a double bond here, this planar system, when you rotate like this, what it is going to be? It is going to go up. That means we get this system. So this is possible. This is possible only when this photochemical conversion of this molecule to this one. That is called provitamin D3. Provitamin D3. That is why you may be knowing that for vitamin D you require sunlight. Why sunlight? This is the reason. You see here. This must come from solar radiation. This cholesterol goes to this molecule and then it comes to provitamin D3. And from there, through a 1,7 sigma tropic hydrogen shift, it comes to vitamin D3. How this one? This is the 1,7 sigma tropic shift. I think you can get it now. And which is otherwise thermally forbidden, but here it is going to take place because of the less strain here. This interfacial shift is possible. And this is a complete example of natural system happening in nature. So that is you just have to take note of this one. That is your D3, vitamin D3. I think you got it. Hello. বুজি পাইছা নেকি?
স্যার ভালকে বুজি পোৱা নাই।
ভালকে বুজি পোৱা নাই? No. Which one? This particular. A2 system. Now 1,7 to বুজি পাইছা? 1,7 is going to be sigmatropic. 1,7 sigmatropic shift is going to be thermally forbidden, geometrically allowed because it is interfacial. But here it takes place because of the larger size. The transition state happens through a larger size, larger ring system, and there is less strain here. And because of this is thermally allowed. Now here, this is a natural system which is there. You just you just see this one is going to give you this. You can just check it using a 3-member ring system. Odd electron system. This one. There are three pi bond. 3 pi bond means odd system. If you apply Todd rule, what it should be? It should be thermally odd, this rotatory. But if we happen to photochemical, it should be con rotatory. And the rotation has to be con because these double bonds are in this position. this H and this CH3 are in this position because our natural molecule which is there are this methyl group and this hydrogen are in trans position. This methyl group and this hydrogen are in trans position. So to be in trans, this rotation of this methyl group and the hydrogen here has to happen in con. Already we have done this electrocyclic reaction. You can see it separately, and you will find it is happening that way. So that is one part. Second part is this one. This becomes now this molecule provitamin D3 becomes D3 through a 1,7 sigma tropic shift. What is this 1,7? This is 1 and 1, so it is 1, 2, 3, 4, 5, 6, 7. The numbers are already given. So this rearrangement shift is going to give us this molecule. And it happens to be 1,7 sigma tropic shift, but we know 1,7 sigma tropic shift has to be photochemical, but here it takes place thermally because the interefficient shift is less strained. So that is the reason. I think you got it. It will be all up fully. If you can see it, you can understand. There is nothing difficult. Let us come to the next one. Co-rearrangement. Here you have to see it very carefully. What is co-rearrangement? Already we know that one. Co-rearrangement is 1,5-diene rearranged to another 1,5-diene via 3,3 sigma tropic shift, known as co-rearrangement. So this is a 3,3 sigma tropic shift, and that also will take place thermally. You can see this one. Upgradation not required. So another 10 minutes, this video will get off. Now you can see this one. This is a 1,5-diene. So 1, 2, 3, 4, 5. This is a 1,5-diene. And the sigma tropic shift is going to be 3,3 because you can just see here 1, 2, 3. And this is also 1, 2, 3. The bond is forming between 3 and 3, so it is 1, 3, sigma tropic shift. All right, and this will take place thermally because here you can see this is one allylic system and this is another allylic system. And homo of two allylic system you will find here. This is going to be allylic system. Homo is going to be of opposite phase. This is going to be here, and another will be also of this. This will be antisymmetric. So if it is antisymmetric, this one also is good. So this is homo of one, another homo of this one, because they have to have. So this is possible here, this is possible. So this transition state is going to be continuous transition state. There is no bond breaking here happening. So this is going to be thermally possible. 3,3 sigma tropic shift. That is the theory. Let us take some example. Now, stereochemistry of this one is very, very important. How to see this one? Let us see this example. Now, suppose this is our diene. Just see. This is very and very often these examples, this examination, this is being set. Various competitive examination also. Suppose this is the diene system. This is 1,5-diene as usual here. But you see this two methyl group which is there are in syn configuration. Is in syn mode, same site. And here it is in the anti conformation. Because here it is single bond, so there will not be any configuration. So this is anti here. These two methyl group are anti, and here these two methyl group are syn. Now, if it is anti, we get the product which is there, that is coming E product. That means this is going to be E The double bond is E configuration. This double bond is also E configuration. E, you know that it is equivalent to trans. You know that. And if it is seen configuration, it's in configuration of this 2-methyl group, what we find here, this becomes Z. You see here, this methyl group is coming this side, this is your, so this is equivalent to C's, and this is also, and this is trans. So this is EZ product we get. How to rationalize this? How do we get this? So I'm just taking explanation of this one. See carefully. See carefully, and once you see this one carefully, you can understand it. Now, this one, what is this one? This is a 6-membered ring system. You can say 1, 2, 3, 4, 5, 6. And what is the conformation of these 6-membered ring? 6-membered ring happens to be in the chair conformation, right? Chair conformation. So this one, so we can write this. This is equivalent to the chair. This bond is not yet formed. Once we have this transition state, through that one, this bond is going to be formed. So the transition state will be involving this, and which will be a 6-member transition state. 6-member transition state. Now, how to place these two methyl group? So how they are appearing? These two methyl group are C's. What is C's? If you remember, 1,2-dimethyl cyclohexane. What is C's position? Axial and equatorial. Yes or no?
Yes, sir.
Axial, and when they are present in axial and equatorial, that time it becomes C's. And what is trans? Trans is going to be axial, which will get converted into equatorial. Okay. So here, because they are in seen, so this 2-methyl group will be, one will be in the axial position and another will be equatorial. Now you see the transition state that is happening, because all reaction passes through a transition state that is high energy. So this is the transition state in the energy diagram. So what is going to happen here? What is going to happen? This transition state, now you just see how this is the one, just break the bond. This bond is breaking. When it is breaking, what is going to be this one? This will have a configuration like this one. And what will be happening to this one? This will come to this one. And what it is, this becomes E and this becomes Z. So your product is EZ product. Got it? Yes or no?
Yes, sir.
Okay. Now come to the next one. If it is anti, this is seen, and here it is anti. If it is anti, then what happens? These two methyl. Same way we do it. Anti is this trans. This is trans. The trans is axial in the cyclohexane. So this is also axial. Let us put and see. The transition will be involving this one. That means this bond will be something like this. This is going to be the transition state. Actually, it is through transition state. Here I have shown it involving all this bond, because arrow is the one which is telling about the transition state. The bond will be, new bond is going to be formed here. But this position will always be there. This one is, so what it is, this is coming as Z, this is also coming as Z. Now if you put 2Z here, just see how it is going to be. The 2Z, this is C, this is Z, this is also going to be Z. Now if these 2Z are like this, then what is going to happen? These two methyl groups will be interacting with one another. That means that it will be sterically, very much sterically crowded. When it is sterically crowded, that means this product is not going to be formed. Because there is other alternative. What is the alternative? This is again the anti. We can put, but it is anti. This axial also get converted into equatorial. So it will prefer to form in this one, because already we know that equatorial trans is more stable than axial because of that reason you already know. So what we find here, we are left with only 2 minutes. So we find here, so this transition state that is going to come here will have a, after the bond is, new bond is formed, the old bond broken in that sigmatropic shift, this is going to be the product. What is going to be the product? This is E, just see, this is trans, so it is E, and this is also E. And if we put our product here, so we find here, so EE product, and which is formed, and here it is not formed. So that is going to be because of the steady impulse. So this is a very, very important step that you have to remember. All right. Anything you have got any query on this one? It's very simple. You have to know this transition state. Anything? Hello? Then I will disconnect now because it is just 1 minute left. I'll disconnect and then again reconnect. So let me come back. And show this code, everything. Stop sharing. And I end the show and we'll join again. I find here now 25 people.